I'm Xingrui. Today I'm going to introduce our recent work, Intrinsic Reward-driven Imitation Learning via Generative Model. This is a joint work with Yuanming and Professor Ivan. And my introduction will follow this outline. First, I will give some background knowledge about the reinforced learning and the imitation learning, and also some representative imitation learning method. Then I will step into the details of our method, generative intrinsic reward-driven imitation learning. Okay, state and actions are two bases of reinforced learning. State can be a summary of experience, which is a sequence of observation, actions, and rewards, or it can be also a representation of observation, and state and actions can be both discrete and continuous. Usually, reinforcement learning is formulated as a Markov decision process. It's noted as a four-tuple, which contains a set of state, action, and a probability distribution, and a reward function, and also sometimes additional discount vector gamma. So the goal of reinforcement learning is to maximize this objective called expected discounted return. So currently reinforcement learning usually successful in some simulation environment because we can afford a lot of trial and it's easy to parallelize. But in many real world systems, it's not work very well because we cannot afford fail and we have safety concerns. And more importantly, the reward engineering is usually difficult. So instead we can learn from the demonstration. A demonstration is a set of trajectory provided by the expert demonstrator. So we can transfer the knowledge from the demonstration to learn a policy or a real function. So we also can consider the limited demonstration like the one-life demonstration in some video games. So the goal of imitation learning is to train a policy that mimics the demonstrations without using any manual rewards. And in the level of supervision strength, the imitation learning can be regarded as a fusion of reinforced learning and supervised learning. And correspondingly, the representative imitation learning method are supervised learning and supervised learning with interactive feedback actions and some inverse reinforcement learning method. The behavior cloning method reduces the imitation learning method as the supervised learning method. Its main drawbacks is called a compounding error problem. It means that a small error on a single step can result in a catastrophic failure in the end. Directed policy learning and data aggregation both requires the rapidly request an expert demonstrator, so it's not very practical. So the goal of inverse reinforced learning is to learn a real function that best explains the expert demonstration. And then generative adversarial imitation learning is one state-of-the-art inverse reinforcement learning method which train the imitation learning method as a distribution matching problem and train the model with adversarial training techniques. And the variation of adversarial imitation learning methods further improve scale by using the information bottleneck regularizer on the discriminator. Currently, the grand challenge of imitation learning methods is that in a high-dimensional environments like Atari Games, most imitation learning methods fail to perform as good as the demonstration, even with many demonstrations. So the research question is that, can we develop an imitation learning method that can outperform the expert from very limited demonstrations, especially in a high-dimensional environment? To address this question, we propose the generative intrinsic reward-driven imitation learning, GIRIL for short. Heuristics is a family of intrinsic reward function that enables agent to do sampling-based self-supervised exploration in the environment, and this is critical to achieve better than expert performance. Here the demonstration level means that we in a game the expert player loses first life, and then the expert level means that we record a demonstration up to the experts consume all the available lives in the game. So demonstration level is worse than expert level, and also we expect the agent to perform better than the expert. So the problem now becomes how to create an intrinsic reward function that can guide an agent to outperform an expert. We know that in the hand-engineered extrinsic rewards are invisible in complex environments. And in the exploration society, Pathak in ICML 2070 proposed a self-supervised intrinsic reward curiosity reward, which uses the prediction error of state as the surrogate reward function for exploration. And this method is very useful for exploration, but if we could consider the very limited state and the actions in the trajectory of one life demonstration, this method seems to overfit to the demonstration, and the generation ability to more diverse environment is limited. So if we can generate more expert level state action data from the distribution of dynamics, we can do sampling based exploration, and this will improve, this will help us to get a reliable intrinsic curiosity reward and for better performance. So we have two steps to reliably learn agents' state and action dynamics for the limited demonstration. First is to infer the optimal actions for the observed state pair ST and ST+1. And we also need to generate a high fidelity future state for the current state and action in a virtual circle. This is to cycle check what has been learned in the MDP. And correspondingly, our model have two submodules. One is the decoder for modeling the forward transition dynamics, and one is the encoder for backward action encoder. And to train the full module, we maximize this objective. The first part of an objective is a conditional VE, which models the forward dynamics and the backward action encoding in a general generative solution. Because the demonstration is very limited, so the forward dynamics is not very precise. The second term, the KL term, is used to guide the backward action encoding, improve its accuracy. So we train the reward module offline for the demonstration, and after training, we use the reward function. We use the learn reward function to guide an agent to achieve a higher score. And this figure shows the reward inference procedure of the reward module. Here the state and the actions data are collected by the agent when he interacted with the environment. So this is an algorithm. We first train the reward module and then do policy optimization with any policy gradient method. And here we use PPO in the experiment. So in the experiments, we evaluate our method on both Atari Games and the continuous control task. In Atari Games, the action space is discrete, and in continuous control task, the action space is continuous. So we compared with the several baselines. including the supervised learning method and the two state-of-the-art inverse reinforced learning method, GAIL and VIL, and also one state-of-the-art exploration method. This figure shows the final score achieved by different methods in the Space Invaders games. We can see that our method achieves a score that is significantly better than expert. So these are the quantitative results. We can see that our method can outperform the expert in all of the 6 Atari games, which is better than all other baselines. And these are the 4 learning curves. To have more clear comparison about the improvements, we normalize the demonstration performance into 1, and we can see that our method in red color achieves a higher performance than all other baselines, and impressively in the Q-Bird games, our method achieves a performance that is 5 times more than the demonstration. We also have a British study about beta, and we can see that in this study, our method is consistently outperform expert in many Atari games. So in the 2 continuous games, both our methods and the exploration method can achieve the demonstration level performance. We also compared with 4 demonstrations up to 10 demonstrations. And in these 4 tasks, our method is consistently better than other baselines. So in conclusion, we have proposed a novel reward learning module that combines action, encoding, and the forward dynamics model into one generative solution. Our method can generate a family of intrinsic rewards, enabling agent to do sampling-based self-supervised exploration in the environment, and this is key for better than expert performance. And our methods consistently outperform expert with only 1 incomplete demonstration in the high-dimensional Atari domain. And as a future direction, it will be apply our method to a hard exploration task. Thank you, and enjoying some demo videos here. Any questions?
Hi, there's questions from the chat. From Wei-Wan, what if the expert made an error?
Okay, the expert make errors. The expert is not a ground truth expert. We just train some advanced policy optimization methods as an expert. So it can make it can make errors. But our method can still outperform it.
So I have one question. Let's say if someone want to give some fake or some adversarial demos, can your methods handle these adversarial demos?
So adversarial attack in imitation learning is interesting. If the demonstration is attacked by some adversarial perturbations, that means the transition in the demonstration would also affected. So then the dynamics model possible be misguided by the perturbations. So I didn't test this for the adversarial attack. Maybe we need to add some robust method against the adversarial perturbation.
Any other questions from other audience, or you can just unmute your mic to ask the questions. Okay, if no questions, we can end this session earlier.